So the next talk is going to be by Donghang. He's from Purdue and he'll be talking about RPM, robust anonymity at scale.
Okay, so can you see the screen? Okay, thanks Pirish for the introduction, and hello everyone. Today I'm going to introduce our work RPM, robust anonymity at scale. So this is a collaborated work with Professor Ankit Kate. Let's start with the problem definition. So in this work, we focus on solving the anonymous broadcast protocol. And so in this problem, we have a group of K parties where each party has a message to send. And the output of the protocol will be a set containing all the messages. And the security guarantee is that adversary should not figure out the source of each message. Namely, we can know the content of each message, but we should not be able to know who sent which message. So this linkability is something that we want to protect. And in general, anonymous communication has a lot of applications, such as, for example, it is a good tool to support freedom of speech, such as whistleblowers. And also in many regions, anonymity is treated as one of the human rights. Also in the cryptocurrency world, anonymous communication can be used to achieve anonymous transactions. And privacy regulations such as GDPR also treat anonymity as one way to provide data privacy. So for this problem, we also have a lot of related works. We have solutions like onion routing, and one of the good example is Tor network. And as we know, Tor network suffers from many problems such as traffic analysis. We also have related work such as mixed network, which usually has long latency. And we also have related works like DCNet-based solutions. So these solutions works very well for small group of parties, but does not work well for large group of parties. Our work actually falls into the category of MPC-based solutions. So we will also discuss the related works very soon. And the random shuffling is actually one approach to achieve anonymous communication. So for random shuffling, if the input is a vector m, and we want the output to be a vector y such that there exists a random permutation pi and y will be pi of m. So this is the system model of our work. Our work is based on secure multi-party computation, and we use secret sharing as the building block of MPC. And we follow a client-server setting, so there are two kinds of parties. The first kind of party are the clients who provide messages to send. And the second category of the parties are called the server. So they will run the MPC protocols to randomly shuffle the messages, then reconstruct the messages. So we also follow the offline-online paradigm here. So we can design offline phase constructions to make the online MPC phase more efficient. For the adversary setting, actually, let's assume n is the number of the servers and t is the threshold of the servers that can be controlled by the adversary. We usually require n to be larger than or equal to 2t plus 1. However, if you require more security properties such as robustness, we will require n to be larger or equal to 3t plus 1. And on the right-hand side, we have our system model. So our protocol are generally divided into 3 steps. On step 1, client will secretly share their messages to the MPC servers. And in step 2, servers will perform MPC protocols to just randomly shuffle the messages. On step 3, servers will reconstruct the shuffled messages and publish them to anywhere they want. So the core idea of this work is like we can achieve random shuffling by performing an unknown random permutation. So this permutation has to be not known by the adversary. So permutation can be represented by a permutation matrix. So you can see this, we have a small example of how to transfer a 3-to-3 permutation to a permutation matrix. These matrices have very good property, like each row and column will contain precisely one single one, and all other places should be 0. With this permutation matrix, the permutation can just be performed using matrix multiplication. So let's start with a small example. Here we have a permutation permuting 5 elements. And the first step is we need to represent this permutation using a matrix. So this is the result. You can see each row and each column contain exactly one element to be 1, and all other elements are 0. So if we have this matrix ready, And if we have the messages that we want to mix, which is A1 until A5 in this example, then we simply multiply this matrix with the message vector, then we can get the permutation result. So the idea here is that in the offline phase, we can just generate a random unknown permutation matrix. So this matrix has to be unknown by the adversary. So we pick T+1 servers. Each one of them can secret share a random permutation matrix. Then we will multiply all these matrices together to get the final permutation matrix. Because they are T+1 servers, so there exists at least one server that is not controlled by the adversary, so adversary have no idea about what is the final permutation. So for malicious security, actually here we need to check that if a matrix is actually a permutation matrix, and there are two checks to verify. The first one is the elements of the matrix has to be either 0 or 1, and the second check is the weight of each row and each column has to be exactly 1. It turns out these checks is very cheap. For a k by k matrix, we only need 2k multiplications, and more details are in our paper. So that is about the offline phase. Then the online phase turns out to be straightforward if we have this pre-computed permutation matrix. So in the online phase, we take the secret shared message vector as the input. Then the online phase is just compute and output this matrix multiplication. Considering M is a vector instead of a matrix, this is essentially just a K inner product. So what's the cost? Here, the round complexity is 2 rounds. The first round is used to do the inner product, and the second round is used to reconstruct the result. And for the computation complexity, it is all of k squared because of the inner product computation. For the communication, actually, it depends. So if the underlying MPC framework support efficient inner product, when I say efficient, I mean like it supports all of one communication per inner product, then our protocol will lead to all of k communication complexity overall. However, if the underlying MPC framework does not support that, we may have to use like Beaver triples to compute the inner product, and this will lead to all of k squared communication complexity. So to deal with this problem, we actually designed the second variant of our protocol to overcome this issue, and we can achieve all of k communication in the online phase as well. So long story short, we just design offline phase construction to move the inner product computation to the offline phase. So it turns out that the first two variants achieve good performance when k is not too large. Let's say when we want to mix less than 10k messages. However, when the number of messages is larger, the offline phase and the online local computation becomes very costly. So we think about how to scale our protocol even more. So here we provide the variant 3 with square network. So on the right-hand side, you can see an example of a 9-input 4-layer square network. Since we have 9 inputs, and you can see there are many squares here. Each small square here actually represents a small permutation. So for a 9-input network, actually each small permutation will take 3 messages as an input. 3 is actually the square root of 9. And we send the output to the next layer in this way, then we do so on and so forth. There exists some research showing that after a constant layer of square network, the result is almost a random permutation, which is more than enough for our requirements. And this round is usually, let's say, 15 rounds. So the random permutation now can be achieved through just after a constant number of iteration. And the computation complexity is reduced to all of k to the power of 1.5 because the input size of the inner product has reduced from all of k to all of square root of k. And we still have round complexity to be a constant, although this constant is a little bit larger than the first two variants. So they provide different trade-offs. Now let's talk about robustness. So if you see, our protocol simply relies on the secret sharing reconstructions and secret sharing multiplications. And if you use Beaver triple techniques, basically multiplications can also be reduced to secret sharing reconstructions. And here, that means if we have robust secret sharing reconstruction, then we can have robustness for our protocols. Oh, by the way, so robustness means even when the adversary doing malicious behaviors, we can still guarantee that the honest parties get the correct output. So it's kind of a strong security property. So it turns out we can do robust secret sharing reconstruction under n to be larger than equal to 3t plus 1 setting using the algorithm on the right-hand side. So the first 3 steps of this algorithm is actually the same as the non-robust version, and it is used to detect if there is any error. If there is an error, it will go to the step 4, where we run the Reed-Solomon decoding to correct the errors and reconstruct the correct polynomial. So basically, you can see the performance is the same as non-robust version. If there is no malicious behavior, we just go to step 1, 2, 3, then that's it. So only when there are malicious behavior, the performance will be influenced, and we see basically the performance decreased around half. So this is a table providing a general theoretical complexity comparison with related work. So the bottom 3 are our protocols. In general, our protocols achieve the best the client-server cost, including both the communication and the computation. And for the server-server communication and computation, actually, we are the good, but we are not the best. For example, Clarion actually achieves better, but the Clarion is not straightforward to provide robustness. So this is about the performance comparison. Then for evaluation, actually, we implement the prototypes using MP-speeds, and we launched some experiments with both offline phase and online phase using AWS instances. And on the left-hand side, you can see the performance result of our variant 2. Basically, this is good for a small case, small number of messages. So it shows we can make, let's say, 10K messages within 0.6 seconds and with 2 megabytes of communication. On the right-hand side, we have the performance table of our variant 3. So this shows that we can basically make 60K messages under around 28 seconds. So this is basically everything I want to cover today, and we can take some questions here. Thanks for listening.
Thank you for the nice talk. I'll have to speak there, right? Yeah. Thank you for the nice talk. And we have one question from Aaron. So do you assume a synchronous network? Basically, do you require a broadcast channel? And if so, how was it implemented? Yeah. Hello, can you hear us?
Yes.
Yeah, okay. So there is a question from Aaron. Do you assume a synchronous network? Do you require a broadcast channel? And if so, how was it implemented?
So in this work, we assume synchronous network, but as you can see, actually, this work it's designed solely on the secret sharing reconstructions. So that also means if you have asynchronous secret sharing scheme, this work should also work on the asynchronous setting. For example, if you initialize our protocols using Honey Badger MPC, which is actually an asynchronous MPC framework, then actually this should also work. So I don't think our work rely on any synchronous or asynchronous assumptions. But for simplicity, let's say it can support. In our paper, we assume the synchronous. Oh, actually, in our paper, we present an application which is anonymous messaging. Basically, we can allow two-way communications. We can have senders send something to the receivers, and receivers can reply to the sender in an anonymous way. So if you think about it, this protocol actually can be easily reversed. So let's say sender sends some messages using a permutation, and the receiver will get it. Receiver can simply find the sender by reversing this permutation. And in our work, actually, reversing a permutation is identical to reversing the permutation matrix. And because the permutation matrix has very nice properties, it's orthogonal. So the inverse of the permutation matrix is just computing its transpose, which is very cheap, and it is local computation in MPC. So we can support this kind of two-way communication very efficient.
Okay, thank you for your answer and thank you for the presentation. Just for reference, in his time zone, it's 3 a.m., so he's giving a presentation at 3 a.m. Yeah. Thank you for the talk.